So now let's examine the spring mass system in English units. So we have an object weighing 10 pounds and it stretches a spring 2 inches and then it reaches equilibrium. So let's determine the equation of motion of free oscillations if the object is released from rest at a position 3 inches below equilibrium. So there's a lot of information kind of packed in this question. First, let's kind of pick out some of the information that we have. We're given that the weight is 10 pounds. You can write 10 lbs. We have the stretch on the spring. I write as S equals 2 inches. Then it reaches equilibrium. So we want to determine the equation of motion if the object is released from rest. So being released from rest just means that your initial velocity is 0 and the position it's released from is at a position 3 inches below equilibrium. So my position at time t equals 0 is 3 inches. And if I put a unit on the x dot, since what is 0, it can be 0 anything, but it's a rate, so it'd be 0 inches per second, or 0 feet per second. Clearly, in English units, we want to write it as all these inches is feet, and the weight being in pounds is fine. So if we recall, some mass hanging on a spring, when it comes into equilibrium, that mass provides a downward weight while the spring provides a restoring force acting upward. If we assume that downward is the positive x direction, in this balance we have that the weight is equal to the restoring force. Here we're given the weight. We have a weight of 10 pounds and our restoring force is K times the amount of stretch, or K times, and we're given a stretch as 2 inches, but to be consistent in the English system, I want to write this in terms of feet. So 2 inches is the same as 2 and 12 feet, or a sixth of a foot. So I get 1/6 of a foot. Now drop the units soon. I find that K is 60 pounds per foot, or I guess you could write this as a pound. You can think of as a slug foot per second squared. So the feet will cancel and we'll end up with 60 slugs per second squared. So let's recall that we're going to have to put all this stuff into our ODE. This mx double dot plus kx is equal to 0 for this mass oscillating on a spring after we give it some initial displacement. So that's why I just knew to immediately find k. And then for the mass, well, we're given the weight, and I know that the mass is related to the weight by W equals m times g. And the weight in this case is 10 pounds, so I get 10 equals the mass, which I don't know, times the gravitational pull in the English system is 32 feet per second squared. So I'll get a mass of 10 over 32, or 5/16. And the unit is a slug, so 5/16 of a slug. So I pretty much have everything I need now to put into my equation. So I really want to solve the DE. So without the application, a problem could just say solve 5/16 x double dot, let me see, plus kx, that's going to be plus 60x is equal to 0, subject to x of 0 equals, again here we have 3 inches, which is 3 and 12 feet, or a quarter of a foot. And since it's released from rest, we'll get x dot of 0 equals 0. And this would be, I guess, a basic math problem. So in solving this, let's consider what we've done in the course. So first, let's go ahead and normalize the x double dot term. So I'll write this as x double dot plus, I guess if I multiply by 16 over 5, I'll get 60 times 16 over 5x is equal to 0. And let me see, if I simplify that a bit, 60 over 5 is 12, and 12 by 16 is 192. X equals 0. And this value is my omega squared, which I know as, well, the square of my angular frequency, which is the square root of k over m. So I know the solution. Let me see, if that's omega squared, then omega must be the root of 192. So I know that the solution, which I write over here, must be x of t equals c1 cosine of omega t, which is root 192t, plus c2 sine root 192t. So I have a condition on the position function that I can impose now, but let's go ahead and find the velocity, because I also have a condition on the velocity. So I get x dot of t, or dx by dt. And if I take the derivative of this first term, let's see, I have a cosine, so I use the chain rule. That's going to turn into like a minus sin sine, and then the chain rule is going to bring out the square root of 192. So I get root 192, a minus a c1, it's not very clear, it is a minus sign, times the sine of root 192t plus root 192 c2 cosine root 192t. Okay, so let's apply that first condition. Apply, given that x of 0 is equal to, so here, 1/4 of a foot. So if I do that, I go back to this first equation here, I get 1/4 of a foot equals c1, the cosine of 0 of course is 1, plus c2, the sine of 0 is 0, so that immediately tells me that c1 is just 1/4. And likewise, if I apply the x dot of 0 equals 0, let's see, I get that 0 equals, so I have the negative root 192 times c1 times the sine, of course, of 0, which is going to give me 0, plus I get root 192 times c2, and the cosine of root 192 t, and t is 0, which is going to be 1. So I end up with 0 equals root 192 times c2, which guarantees that c2 must be 0. So I'm pretty much done now. I'll just write my equation of motion, x of t equals, so I have c1 cosine root 192t plus c2 sine, but c2 is 0, so c1 is 1/4. I get 1/4 cosine root 192t.